Yeah, I'm sorry.
Okay, well,
Yeah, so I should introduce you. So the speaker is Professor Robert Mann from uh, Waterloo University. So he will talk about central charge, criticality, and black hole thermodynamics or holographic black hole chemistry. Okay, Robert, please.
okay, thank you, Mew. And again, the original title is the one at the top, but as I prepared the talk, in some sense, it goes broader than this into what we're understanding as the holographic form of black hole thermodynamics, or what I've come to call black hole chemistry. So let me begin with something that is, I think, probably familiar to everybody that is in the audience here, and that is what happens if you put a hot object into a black hole? For example, a cup of tea, as John Wheeler asked his grad students some 50 years ago. Well, the puzzle with this is that the tea is hot, it has entropy, but the black hole absorbs everything and has no structure. So you've put a hot thing in contact with a cold one, but the cold one doesn't warm up because the black hole doesn't emit anything. So where does the entropy go? How do you preserve the second law? Well, Jacob Bekenstein was one of the grad students Wheeler was talking to, and he realized that if you pour in the tea, yes, it's hot, but it also has mass. And this will increase the mass of the black hole and therefore increase its area. And so he developed this idea that the area of a black hole was related to its thermodynamic entropy. And out of this emerged the subject of black hole thermodynamics, which were formulated shortly afterward by Bardeen, Carter, and Hawking as the laws of black hole mechanics. The zeroth one is that the surface gravity of a black hole is constant over its event horizon. The first law is the energy conservation law, the one that Hawking realized connected black hole thermodynamics with temperature via the surface gravity, and that is that differences in mass between nearby solutions are equal to differences in area times the surface gravity plus some additional work terms related to the charge of the black hole, if it has one, or the angular momentum of the black hole by this term here of angular velocity times the change in J. The second law is what Jacob Bekenstein first formulated, namely that the area of the event horizon never decreases in any physical process. And Werner Israel looked at the third law somewhat later and basically proposed that no procedure can reduce the surface gravity of a black hole to zero in a finite number of steps. So those laws became the uh, laws of black hole thermodynamics. So, what is black hole chemistry? Well, the idea is basically this. In the laws of black hole mechanics suggested that the mass of a black hole was related to thermodynamic energy. The surface gravity of a black hole multiplied by h bar over 2 pi corresponded to temperature in thermodynamics. This is what Hawking demonstrated. And Bekenstein pointed out that the area was related to the entropy. And once the temperature relation was understood, the factor of a quarter of the area divided by h bar came about. It's actually gh bar. Uh, and then we had a correspondence with the first law that dm was kappa dA over 8 pi plus omega dj plus phi dq, the work terms. Thermodynamically, dE is TdS plus VdP plus work terms. But then, of course, what is conspicuous by its absence on the right-hand side is the some analog of a pressure volume term. Where would that be? Brian Dolan pointed this out about 11 years ago now in this paper here. And the answer that has emerged is that the connection with pressure is via a cosmological constant, which Einstein introduced into the Einstein equations in order to obtain a static universe. And he considered it to be his biggest blunder, since Hubble observed the universe was not static but expanding after Einstein introduced, some number of years after Einstein introduced this term. But today it looks like we need it, and it looks like we need it for two reasons. Cosmologically, our universe appears to be expanding, and all the data is consistent with a positive lambda. Alternatively, efforts in constructing a quantum theory of gravity via string theory seem to be very well formulated if lambda is negative. And that turns out to be cosmic pressure, as I will point out momentarily. So the basic idea is the larger the larger in magnitude that lambda is, the higher the pressure of the thermodynamic black hole system. So how does this work? Well, the notion that lambda could be a thermodynamic parameter actually goes back to these papers, one of which I wrote with Joly and Creighton. What we didn't explore at that time was the notion of a conjugate to pressure, which would be thermodynamic volume. So if you take a four-dimensional Schwarzschild black hole, I haven't written down the metric, but if you accept the notion that pressure is negative lambda over 8 pi, or 3 over 8 pi L squared, then the mass, the temperature, and the entropy are all given by this in terms of L and the horizon size R plus. And it turns out the thermodynamic conjugate to P is the Euclidean volume, 4/3 pi R plus cubed, of the black hole. And one can show that both the Smarr relation and the first law are straightforwardly satisfied by taking differentials of these quantities and simply by algebraically combining them like this. And notice the importance of the PV term. M is not 2TS, the relation Larry Smarr pointed out about 50 years ago. We need the PV term in order to recover the Smarr relation for an ADS black hole. The identification of lambda with pressure is naturally obtained if you take the Einstein equations with lambda and no stress energy and put lambda on the other side and interpret it as the stress energy of the vacuum via a perfect fluid model. If I want GAB lambda, or negative GAB lambda, to correspond to this structure here, rho plus P has to vanish and the pressure P has to be negative lambda. And so we do indeed obtain a natural relationship between lambda and pressure, like so. So now, as Castor, Ray, and Trashin pointed out, what they did is they recast the old Bardeen-Carter-Hawking argument, but to include a non-zero lambda. And what they found is that mass and gravity corresponded to thermodynamic enthalpy, gravity and area respectively corresponded to temperature and entropy, as they always have, and geometrically they showed that lambda corresponded to pressure, or rather minus lambda did, over 8 pi g. And so now the first law on both sides had a pressure volume term, a VDP appeared on both sides, and the thermodynamic enthalpy, which is energy plus PV, becomes on this side energy plus PV, or energy minus rho V, where, in other words, the mass of the black hole system is the total energy minus the energy of the vacuum, which both of which are infinite, but a proper integration of both quantities over the entire space-time leads to a cancellation, and one gets a finite black hole mass. And these ideas did appear partially in these various papers here, in fact, going way back to Teitelbaum in 1984, but it was this paper by Castor, Ray, and Trashin that actually formalized this relationship. So how does this work? Well, here is an example via the famous Hawking-Page transition. So here is the metric for a Schwarzschild ADS black hole in d dimensions, a generalization of what I mentioned earlier, where this quantity k would be 1 for an expected spherical black hole. But if this space has flat curvature or negative curvature, then k will respectively be 0 or negative 1. And these solutions are now fairly well known. Well, what Hawking and Page showed is that in contrast to asymptotically flat black holes that evaporate by Hawking radiation, anti-de Sitter space is like a confining box, and so the radiation of the black hole doesn't escape. Rather, a static black hole will be in thermal equilibrium with its own radiation. And a plot of the free energy of the black hole versus its temperature leads to this cusp curve right here, where at high temperatures you have larger black holes, but if you could cool the system down, the black hole would get smaller and smaller and smaller until the free energy hits 0, at which point the thermal radiation of the black hole becomes the thermodynamically favorable state. And so a black hole will dissolve into thermal radiation at cool enough temperatures. Or, turning it around, suppose you had thermal ADS. As you increased the heat of the radiation, you would reach this first-order phase transition point, THP, at which the radiation would condense into a large black hole. If you followed this curve, you would still have black holes. They would get smaller and smaller, but these parts of the curve are thermodynamically unstable to being radiation. And so instead, you have this first-order transition between this gas of radiation, a low entropy state, into a much higher entropy state at this point. This minimum temperature that any black hole, even unstable, could have, that an unstable one could even have, is given by 1 over L. And that's right here. So what David Kubiznak and I did about 7 years ago is show that within the context of the pressure volume tools given by black hole chemistry, this system can be understood as a transition between a solid, which corresponds to radiation, and a liquid corresponding to a large black hole. Now, that might sound a bit counterintuitive, but remember, a solid is a more ordered state of lower entropy of any substance, and a liquid is a more disordered state of higher entropy. So indeed, this is the correspondence. We have a first-order transition across this line from a low entropy radiation state to a higher entropy black hole at any given pressure. And it's known holographically that this phase transition corresponds to a dual, to a quark-gluon plasma phase transition in the dual CFT. It's not hard to write down the equation of state of the system, which is pressure volume is T minus K over V, where K is the curvature of the black hole horizon, plus 1 if the black hole is spherical. You can see that a planar black hole with K equals 0 gives you the ideal gas law that we're very familiar with from chemistry. And the quantity little v is actually related to the total conjugate volume divided by the number of degrees of freedom, which is the area of the black hole over the square of the Planck length, given by this relation here. So, well, that's all well and fine, but what made this subject more interesting is something David and I did about 10 years ago, actually before what I just showed you, where we pointed out that charged anti-de Sitter black holes can be understood as van der Waals fluids. And here I have the metric of a four-dimensional charged anti de Sitter black hole with the mass, the charge, and the cosmological term, and the vector potential associated with the electromagnetic field, negative q over r dt. So it's not too hard to show using standard arguments from Wick rotation, for example, to get the temperature, and the entropy is simply a quarter of the area, or you could get that in a more sophisticated way from the Waals formula. The conjugate electromagnetic potential is q over r plus, and the pressure and volume are still given by what would happen, what you would get even if the black hole were neutral. And it's easy to show that the Smarr relation and the first law are both satisfied. And again, I emphasize that without the pressure-volume term, you would not satisfy the Smarr relation. So you can get an equation of state simply by recognizing that the temperature formula actually is the equation of state when you eliminate L squared in terms of the pressure. And here it is. And noting that the physical pressure is related to the P, and the physical temperature is related to T by these various constants, h bar c and the Planck length, and h bar c over Boltzmann's constant. You can show that the physical pressure is kBt over 2 L Planck squared r plus. And so this is another reason why we make use of the specific volume little v. And so we can write the equation of state as P is T over V, that's the ideal gas part, minus this 1 over V squared term, plus this additional term. This is a form of van der Waals equation. And if you compute from the Euclidean action the Gibbs free energy at fixed charge, you obtain this relationship here between the Gibbs free energy and the horizon size, the pressure, and the charge. And you can plot this function. And you find that when the pressure is sufficiently large, the curve is given by this smooth dashed line. Below a critical value, the curve develops this swallowtail structure, where you have a first-order transition at the crossover point between a large and a small black hole. At the critical point, the swallowtail shrinks to a kink. And that is a second-order phase transition right at that point. What happened to the Hawking-Page transition at G equals 0? Well, it doesn't occur because charge is conserved. And radiation is electrically neutral, so we do not have a Hawking-Page transition. And you can draw the coexistence curve, and you find this is just like a high entropy gas phase undergoing a first order transition to a lower entropy liquid phase. That's the small, that's the large, here's the critical point. It's just like a van der Waals fluid. And if you plotted this for a van der Waals fluid, you would get exactly the same kinds of curves. Now here's a more interesting example that we found afterward, and that is one of a monotonic phase transition, which is what refers to a situation when a thermodynamic system changes from one state to another, and then one that is similar to the initial state if you monotonically vary a single quantity, like temperature. This was first observed by Hudson in 1904 for a nicotine water system, where here we have a plot of temperature on the vertical axis versus the concentration of nicotine in a nicotine water mixture on the horizontal axis, from no nicotine to 100% nicotine and everything in between. So inside the curve, inside this circle, nicotine and water separate into two distinct liquids. Outside of it, they are indistinguishable. So you can see at high temperatures, water and nicotine are mixed. Now, that makes sense because there's so much heat, the molecules are bouncing around each other and they just can't separate. But once the system gets cool enough to about 200 Celsius, if it's about half concentrated with nicotine, then the liquids separate. And then as you cool it even further, down to 60 Celsius, they merge again, and the reason why they do that at cold temperatures is the water polar bonds to the nicotine. Now, this was first seen by Hudson, but it's since been seen in many other systems, as reviewed in this Physics Reports article: gels, ferroelectrics, multicomponent fluids, binary gases, liquid crystals, and, as we pointed out, in black holes. And this was first found by Natasha Altamirano, David Kubasnak, and I, where we looked at a phase transition in rotating anti de Sitter black holes in higher dimensions with two rotations. And what we did is we plotted the coexistence curve for those black holes, analogous to what I showed you for the charged case. And what we found is we actually had two curves, a big one over here and another little one there that I will enlarge. And within this narrow range of pressures, we saw that you could have a large black hole of high entropy, a smaller one of lower entropy, but then another larger one of higher entropy again. Here it is enlarged. We have a large, small, large phase transition, fully analogous to the mixed, separate, mixed transition of water and nicotine. High entropy, lower entropy, higher entropy, just like this. Now, you can't go at a given pressure. It's within this narrow pressure range this happens. At any given fixed pressure in this range, this will happen until, of course, you get to this dashed line. There are no black holes there. The intermediate black holes are really in this triangular region, but it was too big to write, so they trickle out over there. Now, since then, this has been shown to take place in many other examples with black holes that have other features with them. And some of them were pointed here, but lots of people have found this kind of thing. And so I will not, of course, explain the results of black hole chemistry in full detail, but there are lots of them. I already talked about the Hawking-Page transition being like a solid liquid one. Van der Waals fluids are analogous to charged black holes, or perhaps I should say it the other way around. Charged black holes behave like van der Waals fluids. We found re-entrant phase transitions. We subsequently found in this paper black hole triple points, where just the way ice, water, and steam merge together at a particular value of temperature and pressure, so can doubly rotating black holes have three phases that merge together at a particular point. We found after that, not recently, I guess 8 years ago, that some black holes have polymer-like transitions where the critical exponents are not the standard ones of mean field theory. Eric St. Joa, Roby Hennigar, and I showed, along also in another paper with Hannah Dykar, that black holes that have scalar hair can undergo superfluid phase transitions fully analogous to helium-4. In other words, the coexistence line is a line of second-order phase transitions, just like helium-4 when it condenses into a superfluid. Clifford Johnson pointed out that black holes can behave like heat engines. And in this paper with Roby and Fiona McCarthy and Alvaro Ballon, we showed that these heat engines, Johnson pointed out, have a theory-independent upper limit to their efficiency. And you can then use this to maximize the efficiency of a given black hole. It was more recently shown, beginning with a paper by Michael Apples, Ruth Gregory, and David Kubasnak, that accelerating black holes can behave like thermodynamic systems. And this came as a bit of a surprise because an accelerating black hole radiates. But if it is an anti-de Sitter space, and if the acceleration has an upper bound to it, then indeed you can recover the first law and Smarr relation for these holes, and there's a series of papers talking about this listed over here, and they exhibit new phenomena like the snapping of those like the swallowtails that I showed you can snap into other forms suddenly as the temperature or the pressure, depending, hits a particular value. And somewhat recently, Xiaowen Wei and Yuxi Liu thought that maybe all this phenomena is telling us that black holes are molecular in character, that their microstructure certainly seems to behave that way. And I have a paper with them in PhysRev Letters where we pointed out that small charged anti-de Sitter black holes have repulsive microstructure interactions. So let's get to the holographic part. That's really why we're here. Holographic black hole chemistry asks, how can we understand a variable cosmological constant from a holographic perspective? And I'm going to mention 3 ways. A holographic Smarr relation, complexity is thermodynamic volume, and then the promised central charge criticality. So one of the comments that has been made over the years about this is, how can we understand variable lambda in the context of the ADS-CFT correspondence? And the question is this. It was shown long ago by Maldacena that ADS 5 cross S5 seems to correspond or be dual to an n equals 4 SUN super Yang-Mills CFT. And that the near horizon geometry of n coincident D3 branes on this side gives this kind of relation where the ADS length is related to this n, not that one, but this n of the super Yang-Mills multiplied by the 10-dimensional Planck length times this root 2 over pi squared. So if pressure varies, L varies. But if L varies, it looks like N has to vary. But how does that work when the N is the N of SUN? Well, variable pressure is variable lambda. Some have indeed, like Johnson and Dolan and Castoret and Trashin, have suggested that maybe N, or rather N squared, is indeed a thermodynamic variable and having a conjugate chemical potential for the color. But Karch and Robinson suggested that maybe we should look at this in terms of a variable field theory volume having a conjugate gravitational coupling, because this Planck length is related to the d-dimensional or 10-dimensional gravitational coupling. So I'm going to look at that. We have this relationship here in 4 dimensions, which is what they worked with to illustrate. At large n, the thermodynamic grand potential should scale like n squared on dimensional grounds. And from this, you can obtain, by taking derivatives on both sides and using Euler's relation, you can show that there is this relationship, this holographic Smarr type relation between the energy of the CFT, temperature, entropy, phi and q, omega and j, and the central charge and a conjugate quantity mu. And the equation of state turns out to be given by this rather simple relationship right here. Cedric Sinamuli and I showed that this can be extended to higher powers of n via Lovelock gravity, where the g's are polynomial functions. And because the Lovelock couplings have this dimensional scaling relation, the g's must go like this in order to preserve the dimensionality of this grand potential. And by using the Eulerian relation on both sides, we were able to obtain the bulk Smarr relation using this logic, where the alphas are regarded, the alphas are the Lovelock coupling constants, regarded now as thermodynamic variables with conjugate quantity psi. And these are the various charges of the black hole and phi's, or other work terms as the case may be. Where do these g's come from? Well, we pointed out that the n squared term of Karch and Robinson comes from this closed string type diagram, and the higher orders, or rather I should say the higher orders in 1 over n, come from this diagram, which is the n to the 0 case, and the 1 over n squared case comes from this diagram, and so on. And in general, we pointed out that the kth order term goes like n to the exponent 2 times 1 minus k. So that's a brief sketch of the holographic Smarr relation. But more interestingly, we recently studied the notion of complexity of black holes from this black hole chemistry viewpoint. Now, it was pointed out a few years ago by Susskind and collaborators that perhaps there is a relationship between the quantum complexity of a boundary state of the CFT at some time slice in the bulk. And in particular, two conjectures were put forward in these papers. One is that this quantum complexity. Sorry, is there a question? Okay. One is this quantum complexity becomes, oops, sorry, is related to the volume associated, with this time slice of the interior here. It's the volume of an extremal codimension 1 slice B, and R is some arbitrary light scale, G is Newton's constant. The other proposal is that if you take this time slice and extrapolate the forward and backward light cones from each point, you get a patch inside the bulk, a space-time patch known as the Wheeler-DeWitt patch, which is the domain of dependence of the Cauchy slice, both in the past and in the future. And IWDW is the action on this domain. And both seem to have the right scaling properties for quantum complexity. So various people have explored this. It's quite a difficult calculation to do, as pointed out in this paper here by Lehner, Myers, Poisson, and Sorkin, because there are divergences, there are edge terms, there are corner terms, all of which have to be carefully calculated. And in fact, the relevant quantity is the difference between the black hole ADS and pure ADS in both cases, be it the volume of the extremal codimension 1 slice or the action of the Wheeler-DeWitt patch. Now, various studies of these quantities led to this general expectation that the complexity scaled like the thermodynamic entropy of the black hole. But this was based on calculations for charged spherically symmetric black holes. What we find is this is not correct in this pair of papers here that I have with Rahim Al-Balushi, Roby Hennigar, and Harry Kunduri. We find that instead it scales with the thermodynamic volume, which is particularly evident if the black hole is rotating. Both have this log 1 over T term, but the coefficient is different once the black hole is sufficiently large. So let me sketch out what happens. I already showed you for charged black holes, the entropy was pi r plus squared, the volume was 4/3 pi r plus cubed. Now, volume and entropy are not independent here. They both depend on the same parameter. So one is a function of the other, and that carries over to higher dimensions like so. There's a degeneracy between these for most, not all, but most spherically symmetric black holes have an entropy volume degeneracy. But for rotating black holes, this degeneracy is broken. And so we set out to study this. As shown quite some time ago in this paper, the entropy, well, actually earlier than this paper dealt with the volume. The entropy of a rotating black hole goes like, has this dependence on R plus in the rotation parameter, whereas the volume is a different function of R plus in the rotation parameter. These now become two independent functions when the black hole rotates. So that opens the possibility of understanding what complexity is in this context. Now, what we found is this is a difficult calculation. Rahim and I started it, but the null hypersurfaces are very complicated functions of the polar angle as well as the radial variable. So it's not clear how to construct either this extremal slice or the Wheeler-DeWitt patch. Furthermore, caustics can form if they're charged, if the black hole is charged and sufficiently large. But if you look at multiply rotating black holes, the problem radically simplifies if the angular momenta are all equal. And so that is what we looked at. Here is the metric for these black holes. The key virtue is all the metric functions have no angular dependence. They only depend on the radial variable r. And so the Wheeler-DeWitt patch again becomes analogous to that of a charged black hole, and the calculation becomes tractable. The curvature of this space here, it's an Einstein space given like so, and just to illustrate what G hat and A would look like in the simplest case when n is 1, capital N is 1, D is 5, this is just the metric of a two-sphere, and A is a half cos theta d phi. These become more complicated in higher dimensions, but we did them. They are known in these papers. So the null hypersurfaces, as I said, are calculable. The horizon generators are well understood. And what do we get? Well, I've put down the complicated formulas for the complexity here in terms of the this is the action minus twice the anti-de Sitter action, twice because you've got each side here. It's given by this integral, which is a bit awkward, and this other integral here over this function and these terms due to the edges and corners. But the net effect when you calculate all of this is that we got the answer to behave like a power. Well, we didn't try to get this. We discovered the answer went like a power of the volume to the d minus 2 over d minus 1, divided by the ADS volume. And to demonstrate the striking difference compared to expectations with entropy is here is the 5-dimensional case. To be concrete, these different colors correspond to black holes of increasing size. Now here I plot the complexity in the action conjecture divided by v to the 3/4, which is d minus 2 over d minus 1 when d is 5. For large black holes, you can see they all scale to be a constant as the black hole gets closer and closer to extremality. It's not so good down here for small black holes away from extremality, but for larger ones near it, and even large ones far from it, this relation is very well satisfied. Whereas if I divide Ca by the entropy, then there's no scaling whatsoever at all, and there is no convergence the way there is over here. The same thing happens for the complexity equals volume conjecture. The formula is a bit easier, and again, when we compute this using the equal rotation multiply rotating black hole, we again obtain this value, and again can plot the curves. For small black holes, the relationship is not great, but we don't expect it to be. But for large black holes, it converges very, very well, whereas this is not the case for the entropy. The black holes are getting bigger and bigger this way, and here, although this looks like convergence, it's actually not in the size of the black holes. This is well separated. They just look close together because of this scale. So and we checked, this is 5 dimensions, but we have checked this all the way up to 27 dimensions numerically. And here is what the volume scaling looks like for these various exponents. And here is when we plot CV relative to R plus to a power, we find these powers beta very well agree numerically with what we would get from this formula. And so the lesson is that complexity of formation scales with thermodynamic volume, not thermodynamic entropy. And there are partial results for the Kerr ADS and BTZ solutions shown in this recent paper by Benamonte and collaborators, and for solitons as Shane Andrews, Roby Hennigar, and Harry Kunduri showed. So why volume? Well, the meaning of thermodynamic volume is related to this puzzle that asks, what is the smallest area enclosing a given Euclidean volume? The answer is a spherical surface. And you can construct this ratio of volume to area rescaled by this parameter here for a unit sphere and this factor d minus 1, and you can show geometrically this quantity is always less than 1. Well, you could just replace V for black holes, V by the thermodynamic volume, and A by a quarter of the entropy, or rather, the entropy is a quarter of the area, so A is 4 times the entropy. And Fedich, Gibbons, Kubiznak, and Pope found that for a large number of black holes, they had R obeyed the reverse isoperimetric inequality, that it was always larger than or equal to 1. And if you compute this for a Kerr ADS black hole, indeed, you get this quantity, and it's larger than 1 unless A is 0. And so what they posited that this meant is that if you give me the thermodynamic volume of a black hole, the best way to maximize, well, the way to maximize the entropy is to have it be the Schwarzschild ADS solution, because that achieves this lower bound of 1. So that means that the reverse isoperimetric inequality indicates that complexity is bounded by entropy multiplied by a parameter. The complexity is never smaller than the entropy of the black hole. So entropy still plays a role, it's just not the one people thought that it played. It scales with volume, but it's bounded from below by black hole entropy. So finally, I'm almost at the end.
Yeah,
what about central charge? Pardon me?
So you have 10 minutes.
Okay, yeah, I'll finish easily. So Wan Kong, David Kubiznak, and I, in this recent paper, looked at the holographic Smarr relation and noticed that, again, as I showed a number of slides earlier, the central charge scales like L to the d minus 2 over G. So we looked at the CFT first law and inserted this relation into it and discovered that you get the bulk first law provided you allow G to behave as a thermodynamic variable. And here, the relationship between the tildes and untildes are given by this quantity. This is necessary in going from the boundary into the bulk. So we get the bulk first law. And furthermore, we get a bulk Smarr relation from the a CFT Smarr relation, like so. So what we did is we say, well, what does variable G mean? Well, let's take it seriously by eliminating it in terms of central charge and pressure. Because remember, C goes like a power of L divided by G. Well, a power of L is the pressure. It's L to the d minus 2. So delta G over G is minus 2 over d delta C over C minus d minus 2 over d delta P over P. So we can get rid of this in terms of pressure and central charge and obtain a mixed bulk first law, where now the conjugate volume is different from what we had before. It's actually given by these quantities right here. And the conjugate chemical potential in the bulk is given by this quantity mu. This V satisfies the reverse isoperimetric inequality, provided the chemical potential is negative. And then what we did is we looked at the free energy, both for charged black holes, charged ADS black holes, both the one David Kubiznak and I looked at in 2012, and the one you get from this bulk boundary relation. And we found that the swallowtails in the bulk have a dual in the boundary. And just the way that decreasing pressure leads from no phase transition to a second order to first order phase transitions at low pressure, Likewise, small central charge has no phase transitions. There's a critical one where there is a second order phase transition, and then at high central charge there is the first order phase transition. So this is the first time that we have had a duality of this van der Waals phase transition between bulk and boundary. But there are open questions. What exactly does it mean to vary G? And what would the duals be of re-entrant transitions, triple point, superfluids? How do we incorporate higher 1 over n order 1 over n corrections? Well, we looked at some of these issues in this paper with Mannes Visser. Right here, it's and Mannes Visser looked at it himself here. This has now been published. I forgot to update it. It's in JHAP. So in summary, black holes behave like chemical systems. They replicate the phase transitions of other chemical systems, suggesting an underlying molecular structure to their degrees of freedom. A holographic understanding of them is emerging via the Smarr relation, holographic complexity, and the criticality of the central charge. But we need to find the dual phenomena to all of this standard black hole chemistry. And if you don't like negative lambda, there's a lot to be done with positive lambda for de Sitter black holes. But I think I've used up my time, so I thank you very much for your attention and for your patience.
Okay, thank you, Robert. So we have some time for few question or comment.
Okay, I have a question.
Okay.
Sure.
So you said that the complexity scales the volume of a black hole, and the lower bound of the complexity is given by the beta S. S is just the entropy. So if I want to know,
beta is a coefficient that you can calculate.
Okay. So, anyways, I want to know what is the corresponding thermodynamical quantity with for the complexity. The complexity is the only variable in the black hole physics.
Well, I'm not sure I quite understand the question. I sketched over what complexity is. Let me see if I can easily go back to that slide. Oops, I stopped sharing for some reason. Let's go here. If I go back to that slide, the complexity is here we go. It's the quantum complexity in the CFT, which is defined as the minimal number of gates, minimal gates that you need to go from a given state in the CFT to any other state. And quantum information theorists have developed ways for calculating this that I did not discuss. So it's not a thermodynamic quantity per se, it's a quantity related to how complicated the information is in the CFT, if you like. What happened was, in these papers here, Susskind and collaborators noted that if you look at how complexity scales, there's a similar scaling relationship with both of these quantities, and that's what led to this conjecture. Now, what we found, as I say, the calculations showed that it was entropy, but we found when we looked at multiply rotating black holes that it went like volume. We didn't set out to prove this, we discovered it. We actually wanted to see what rotation would do, because S was non-trivial, and we tried to get it to scale with S, and it didn't. And then we discovered by accident that if we had it go like volume, it worked. And that's what happened. Does that help?
Okay.
Okay. So, is there any other question?
Can I ask? Yeah.
Yeah.
So, I mean, since you are using the aerial radius, when you write down entropy as a 4 πr square, it's clearly proper. Yeah? But your volume formula doesn't appear proper.
I'm sorry, I didn't get that. The volume, you mean the volume of the thermodynamic volume of a black hole?
Yeah, at the beginning, yeah, just 4, 5. I mean,
Do you mean this one right here?
Yeah, especially when A is 0, the simplest case.
Well, when A is 0, then this does become 4/3 pi r plus cubed.
Yeah, so as if it's like a flat space time. So I'm a bit
Well, it
puzzled.
is. That's what it comes out to be. And that's you can get it in two ways. One, if you believe the pressure is negative lambda over 8 pi, then in order to satisfy the first law, the conjugate volume must be the Euclidean volume for a charged spherically symmetric black hole. Other spherical black holes, it sometimes is different, but for those two cases, neutral and charged spherical black holes, it is the Euclidean volume. You can show it another way. This is what comes out of the Castor-Ray-Trashin work. They reconstructed the Bardeen-Carter-Hawking argument, which is a geometric argument to get the laws of black hole mechanics, but they included non-zero lambda. And from that argument, they developed a geometric formula for the thermodynamic volume, and it agrees with the one I just said. For the simple cases I told you, it is indeed the Euclidean volume. That comes out. It's not something you put in.
But in your metric, don't you have some non-trivial GRR component?
But you don't match the volume in the same way. It's a thermodynamic volume. It's not a physical volume that you match to. It's a volume in it's a quantity in thermodynamic phase space.
So as a conjugate variable to pressure, as you
that's right. That's right.
Okay.
Now, in the real world of chemistry, it is the real world volume. But in the black hole land, it's this funny quantity here. And if you have scalar fields, for example, then it is different yet again. It's only in the simple cases I showed early in the talk where that you get this simple answer, right? But that is a bit unusual. It's the exception as opposed to the rule.
Can I ask one more question?
Fine with me if the organizers say
Yeah,
so.
okay. So we will discuss in the break time because of some delay. Yeah,
Okay.
yeah, I'm sorry. So thank you.
Feel
Robert.
free to email me then.
Okay.
Thank you.
Right. So because of delay, so we will have a 9-minute break, and then we will resume at 11:40. So if you have some question, you may discuss in the break time. Okay.
Can you continue?
I can stay on at the break if you want to keep asking.
Okay.
But go to the break. People should go to their break.
Okay.
Your talk was very interesting, so I'd like to ask some more questions. So in the usual statistical physics, either in canonical or grand canonical ensemble, can you hear?
Yes. Mm-hmm.
So the fundamental variable for the partition functions are volume and temperature, and pressure is conjugate variable. You compute from a partition function. So is the van der Waals equation.
Pardon me?
So same is with the van der Waals equation. You can express pressure as a function of temperature and volume, but I'm questioning the inverse problem. And in your also gravitational setup, it looks like pressure is more fundamental than volume.
Well, I'm not sure how you would define fundamental.
In the sense of multivaluedness. So in the statistical physics, you can show that there are some regions where the volume can be multivalued for given pressure and temperature. So in the sense of multivaluedness, whether it's allowed or
I mean, it is. I'm not sure I entirely understand the thrust of the question, but it's true that volume is a multi-valued function of pressure in general, but that's true in the real world. If you have a van der Waals fluid, maybe I wondering if I can share the screen
But
here.
my question is it still same in the gravitational computation?
Yeah. Yeah.
It is.
So if you plot, I mean, if you plot, yeah, what I mean, if I could take the indulgence of sharing my screen here. Oh, for goodness sake! All right. I'll see if I can. If you allow me to share the screen, then there, if you should be able to see my scribble, and if I plot pressure versus volume, for a van der Waals fluid, you get a curve like that. And the interpretation is that if you shrink the volume, then you reach a point where you'll go like that, where this area is equal to that area. And what's happening there is the gas is condensing into a liquid along this line, and so the pressure is constant. But if you turn this, of course, that's pressure versus volume, and that quantity is single valued. But if you turn it the other way around, so that you plot volume versus pressure, then you'll get something like that. And yes, it's multi-valued, but that happens in a van der Waals fluid, and a charged black hole has exactly the same kind of curve as that. So maybe I hope I'm getting to your question, but maybe I'm not.
So I mean, as you said, I mean, this is about Maxwell construction, and there
that's Maxwell's equal area law. Yeah.
Volume is multi-valued, while pressure is always single-valued.
Right? Well, I mean,
in your diagram, pressure is always single-valued.
It's single valued in all the substances I know of. Maybe somebody somewhere in condensed matter physics has discovered systems that are at one volume can have two different pressures. I don't know, but in general, we find that it is a single valued quantity. I mean, because it is like it's a fundamental constant in the Lagrangian. That's how it's interpreted. And in fact, all the Lovelock couplings, David Castor showed this, maybe with Jenny Trashen, I forget. But anyway, they showed that if you have Lovelock gravity, all the Lovelock couplings can be interpreted as thermodynamic parameters. Lambda is the zeroth Lovelock coupling, and that's the pressure. The other ones correspond to Gauss-Bonnet, that's alpha 2, and third order Lovelock, and so on. Newton's constant, though, was kept fixed as a reference. And what we've discovered in central charge criticality is that it should not be kept fixed. And that's what allows us to get the duality that I showed you at the end.
Yeah, at the end, that is also quite interesting. Have you thought about some dilaton gravity? I mean, it seems to suggest dilaton gravity.
Have we thought about what? I didn't hear.
Dilaton gravity, like Browns decay.
Well, for central charge criticality, no. We just started doing this over the past year and a little bit.
Variation of the Newton constant sounds like dilaton gravity.
It does a little bit, yes. We have looked at, but there's a difference. Well, I don't know, right? I mean, I was about to say there's a distinction between varying a scalar and varying Newton's constant. But maybe one could show that you could ultimately recover this with a scalar. I don't know. It looks like the next speaker is getting ready. Ranjan.
Thank you very much. Yeah, that's very inspiring.
Okay,